Sorry, Intan-san. May I check my slide again?
Yeah, sure. Just test it before you start.
Okay. I want to share some so now you can see at the big screen of my slide, right?
Sure.
Okay. So wait a moment. Could you hear the sound of this video?
Sure. You can hear it.
Okay, nice. Okay, but I don't want to show the sound because it's Japanese language. Okay.
For later. Okay, we're gonna start now.
Okay, good. Thank you.
Okay, so let's just start. Assalamualaikum warahmatullahi wabarakatuh. Good morning, all participants, all lecturers, and students from Green Technology course. Thank you for joining us today. My name is Intan, as the lecturer at Nanotechnology Engineering Department, Faculty of Advanced Technology and Multidiscipline, and now I will act as the moderator in today's webinar. And today, Green Technology course is in charge for DECOTA, video conferencing with Universitas Airlangga. And here we have a distinguished guest lecturer, Dr. Chitipon Choi-Chang from Kyushu University, Japan. So hello, Sawadika, Dr. Chitipon. We are really excited to have you here. How are you doing?
I'm good. I'm doing well. How are you?
So this is your first time coming to our university virtually, right?
Yes.
Apart from that, we actually have another ongoing research collaboration with nanotechnology engineering. Well, I hope you will have a good time, even though it's only a virtual class. All right, beforehand, I would like to introduce a brief CV of our speaker. So here is Dr. Chitipon Choi-Chang. Am I pronouncing your name correctly?
Yes, it's correct.
Okay. His nickname is Song, and I always called him Songkun because he's just my junior. He is originally from Thailand. He completed his bachelor and master degree in chemistry at Mahidol University, Thailand. For his PhD, he graduated in 2019 from Kyushu University, Japan, at Earth Resources Engineering, specializing in environmental system engineering. So Dr. Chitipon is an expert in the field of material chemistry, focusing in two-dimensional materials and natural materials for photocatalysis and catalytic wet oxidation, adsorption, as well as immobilization. The purpose of these nanomaterials are for wastewater remediation, catalyst, photocatalyst, clay-based nanocomposites, and also waste utilization. Currently, he is working as a special assistant professor at Kyushu University to perform some projects as well as develop new photocatalyst nanocomposites, right?
Yes.
So far, he has published around 15 papers with 86 citing articles. Wow, that's such an achievement. Okay, that's a brief profile of him. So for all the participants, if you want to ask the question, please do not hesitate to type it on the Q&A button. And now, without further ado, I will turn the time over Dr. Chitipon. So, Dr. Chitipon, time is yours. Please start.
Thank you very much. Okay. So, okay. Could you see my slide now, right? Okay, so thank you very much, Dr. Intan, for your kind introduction and inviting me as a guest speaker in here. So first, I want to say, Selamat pagi, Universitas Airlangga. Is this right? Good morning, everyone. My name is Chitipon Choi-Chang from University. Today, I would like to give a talk about nanotechnology, especially for the photocatalyst composite and its application for the wastewater remediation. Also, I will show you some of our research achievements about fabrication of the nano material for wastewater treatment. So firstly, I would like to introduce our university. Kyushu University is located in the Kyushu Islands. And if you look at in the map, you can see around here is Fukuoka City. So this is the location of the Kyushu University. And I belong to the Department of Earth Resources Engineering, which consists of the 7 laboratories. For me, I'm working at the minerals processing, recycling, and environmental remediation laboratories. Our research target are the minerals and the material energies, also wastewater treatment. So here, I put this picture, which was taken when the Dr. Intran and I were the PhD candidate at Kitchu University. So let's begin with the question, what is nanotechnologies? Yes, when you see the word nanotechnology, you may think about the smaller thing because of the nano word. Actually, the concept of the nanotechnologies are not new to the nature or to the mankind, but the nanotechnology words was used to describe the size or technology of the processing or building part with the nanometric tolerance. So, do you have any idea how is small of the nanostructure or nanomaterial? Yes, if you look at into your body or the Albert Einstein picture as I show here, what do you think about what is the smallest part that you can find? Yes, some of you might think about the hair, right? The hair of Albert Einstein, if we considering about the size of a single hair, the width, okay, the width of the single hair is approximately about 0.1 millimeter, which is equal to the 100,000 nanometer. Yet it's still big for the nanostructure. And then if you look at inside of the component of the hair, you may can find some cell which had a size about 6,000 nanometer, and the cells was composed by the many DNA where the cell assembly process. The size of the DNA width is about 3 nanometer. So this is an example of a nanostructure that we can find in nature. So how we can conclude, so now we can conclude the nanostructure or the nanomaterials can be referred to the structure or the materials who have the characteristic length scale or a size in the dimension, 2 dimension or 3 dimension that are in the nanometers, when the 1 nanometer is equal to around 3 to 4 atom weight. And when the material are in the atoms or the molecules level or the nano level, it will be exhibit the novel or unexpected property behaviors or phenomena such as the DNA or hair. So in this slide, show the scale of thing. As you can see in the nature, the nanostructure or nano size was can be found such as the atoms of the silicon here, or DNA, or the ATP synthase, which is the M size. Yes, and while the humans also can produce the nanomaterials, for example, carbon nanotube here and carbon buckyball here. So the challenge fabricated and combination of the nanoscale building blocks to make the useful devices, for example, photosynthesis reaction, semiconductors storage. So in this slide, I would like to show you the classification of the nanomaterials. The nanomaterials can be classified into the different scope based on the various criteria. Generally, nanomaterials can be categorized according to their dimensionality, morphologies, state, and chemical compositions. So based on their dimensionality and an overall shape of these materials, nanomaterials can be further divided into the four groups: 0 dimension, 1 dimension, 2 dimension, and 3 dimension. Oh, so sorry. Sorry. Excuse me, Intan-san, could you see my screen now?
Yes.
Okay. Sorry. So based on the dimensionality and overall of shape of this material, nanoparticles or nanomaterials can be further divided into the four groups: 0 dimension, 1 dimension, 2 dimension, and 3 dimension. So for the 0 dimension, the nanomaterial have all the dimension in the nanoscale, for example, size below the 100 nanometer. Sorry, some problem come from my screen now. I cannot point. I cannot use laser pointer now. Sorry, it seems like maybe I cannot use laser pointer to point out that I want to point in the screen. So let's go back to the classification of the nanomaterials based on the dimensionality. So I already explained to you based on the dimensionality, we can classify into the four group: 0 dimension, 1 dimension, 2 dimension, and 3 dimension. For the 0 dimension nanomaterials, or sometimes we call the 0D. It has all the dimension in the nanoscale. For example, the size below the 100 nanometers. The 0 dimension include the spherical nanomaterials, cube, nanorod, and polygon. Also the cold shell nanomaterials, as well as the quantum dot. And one-dimensional nanomaterials or 1D materials. The 1D materials can refer to the material with one dimension not in the nanoscale, while the others 2 dimensions are in the nanoscale. So 1 dimension materials or 1D materials include metallic, polymeric, and ceramic, nanotube, and nanorod filament or fibers. For the 2 dimension nanomaterials or 2D materials, it contains only 1 dimension in the nanoscale, while the other 2 are not. The 2 dimensions include the single layer or the multi-layer, crystalline or amorphous, or thin film, or sometimes you can see like a plate-like structure. And for the 3-dimensional materials or 3D materials, the 3D material has the variant dimensions beyond the 100 nanometers. The 3D materials combine multi-nanocrystal in the different direction. For example, the same the example of the 3D material is like a fibers or carbon nanotube or carbon fibers, fluorines, or some like layer skeleton structure. So if we think about the morphologies, the morphological nature of the nanoparticles include the flatness, sphericity, and as well as the aspect ratio. And for the state, as per uniformity or the state, the nanoparticles or nanomaterials can be classified as isomeric or inhomogeneous or dispersed and accumulated particle. So based on their chemical composition, the nanomaterials can be classified into the variant categories such as the single nanoparticles or nanocomposites, and which are further type. So how we can get the nanoparticles, or how we can prepare the nanoparticles or nanomaterial? Okay. So this slide show the general two synthesis way of the nanomaterials. So generally, it has a two-way to synthesis and to synthesize nanomaterials, including bottom-up and top-down approaches. For the bottom-up approach, the nanoparticles or nanomaterials are first obtained at the atomic level and then integrated into the design materials. So this includes the formation of the nanoparticles from the colloid dispersion or the formation of the powder from the soil methods. And also from the top-down approach, the bulk materials at the microscopic level, which is a very big comparison nanostructure, is cut down into the design nanoparticle level by different means. Some example of this are the ball mill or grinding or PVD. So why do we want to make a thing at the nanoscale? As we know that nanotechnology is advanced area of the research that allow for the production of a wide class of the material, including the particulate, the material with at least one dimension or less than 100 nanometers. So we need the materials to be nano-sized because of making better products, such as the smaller, cheaper, and faster, and more effective, which is contribute to a sustainable future. Also, when the materials are in the nanoscale, some new physical or the phenomenal property can be observed, such as the surface plasmon resonance of the metal nanoparticles or the quantum behavior. So in this slide show the comparisons property of the nanomaterials and the biomaterials. In the biomaterial, the physical property are independent of the size, whereas in the case of the nanomaterial, different physical property can be dependent on the nanomaterial size or shape. And the importance of the nanomaterial was realized when the researcher found that the size influenced the physical chemical property of a substance, including the chemical, electrical, mechanical, and optical property. So nanomaterials have attracted considerable interest because of their unique property. And what will nanomaterials do for our society? So nanoparticles or nanomaterials show the potentials for the several applications, including for water treatment, plant or refineries or industries process or catalytic process also. Sometimes we use the nanomaterials for the drug delivery. So today I will focus on the nano photocatalyst material for environmental purpose, mainly wastewater treatment. So basically, what is a photocatalyst? Photocatalyst is give us methods which can be utilized for the various purpose, like a degradation of the various organic pollutant in wastewater, antivirals and antifouling, and cell cleaning of the civil engineering materials. So to compare with other methods of the treatment process or purification process, the photocatalysis is rapid, growing, and gain more attention from the researcher due to its several advantages, such as the low cost, attractive efficiency. So the photocatalysis is a unique process for solving the energies and environmental issue. So some of the practical application of the photocatalyst are about anti-foxing or cell cleaning. So some kind of photocatalyst, such as a TiO2, can be utilized as a white pigment to coat on the surface of the original building materials to provide the anti-foxing and the cell cleaning property of the building. So the utilization of the photocatalyst as a pigment is useful for the new technology of the cell cleaning building. Also, the photocatalytic treatment process can be applied for the decomposition of the volatile organic compound or VOC, for example, butanols, formaldehyde, or carbon disulfide, to the harmless byproduct by breaking their molecular bonding. So this process will help combine the organic gas to the form of the single molecule that is not harmful to the human, resulting to the enhance the air cleaning efficiency. Moreover, photocatalysis can apply not only gas phase, but also work well in the aquatic system. So the photocatalyst can enhance the mineralization of the organic pollutant to the carbon dioxide of water. Also, it can sterilize the certain bacteria in the wastewater. So the technology is very effective at removing further hazardous organic compounds in wastewater and killing the various variety of the bacteria or some virus. So this slide show about the practical reactor of the photocatalyst, as you can see in this slide. Normally you can see here is a photo. The blue picture is a real photocatalytic reactor produced by a Japanese company. So in this process, the waste water or waste air or toxic air was fed into the photoreactor under right irradiation. So the pollutant can decompose to the small molecule and the harmless byproduct. And I want to show you some video about photocatalytic reaction that we perform in our lab, which in the batch scale. Sorry, this video is in
光
Japanese.
触媒を用いて、こちら
Yeah.
のローダミン B という色素を分解します。
But you can see when we use the photocatalyst, when we use photocatalytic reaction, we can decompose the organic dye. The organic dye is a pink color. So within the short-term reaction and the mild condition, we can decompose the organic dye into the like a water in here that I show you, which is a very fast reaction and effective process to apply for the wastewater treatment. So now you may see what the photocatalyst can do, and you may have some question about what is a photocatalysis. The photocatalysis is the union of the photochemistry and the catalyst. The word of photocatalysis is composed of the two parts. The prefix photo means light or energy in form of light. And the catalysis is the process where the substance involved in the changing of the rate of the chemical reaction. So the substance which is known to be catalyst increase the rate of the reaction by reduce the activation energy or the EA of reaction. So photocatalysis can be defined as a catalysis driven acceleration of the line-induced reaction. And photocatalyst is a material which absorbs light to bring it to the higher energy level and provide such energies to reacting substance to make a chemical reaction occur. So for the history of and the background of the photocatalyst and photocatalysis also, the photocatalysis has been found with the test of the TiO2 or titanium oxide by the Japanese scientist Akira Fujishima in 1972. For the photocatalyst semiconductor, the important electronics level of the conduction band and the conduction band and the valence band was shown here, and the gap between the conduction band and the valence band called energy band gap or band gap. So at the moment, there are many materials has been investigated at the photocatalyst. For example, graphite carbon nitride or CTN4, bismuth oxyhalide, copper oxide, which can respond in the visible light region and highly available for the contribution to the global environment. So how photocatalysis or photocatalysis work in the environmental treatment process? From the previous video, you can see the photocatalysis is very strong process to decompose the organic pollutant in wastewater that change the pink color to the transparent color. So in this process, the strong reactive oxygen species, such as the hydroxy radical or the superoxide radical, can be produced, and it had the strong oxidizing power responsible for the degradation of the pollutant in wastewater. So in this slide, show the principle of the photocatalytic reaction. It's very simple that the reaction will happen when the catalyst will receive the photon energy from light source. And the photocatalytic treatment requires three components: photon from the energies from the light, and you can see the yellow color here, and the catalyst is a red ball here, and the target pollutant. So in the detail of the photocatalytic mechanism, the photocatalytic reaction primarily depend on the light energy and the catalyst. So here, show the fundamental step in the process of the semiconductor photocatalysis. Firstly, when the light energy in the term of photon fall on the surface of the semiconductor, and if the energy of the incident ray is equal to or more than the energy band gap of the semiconductor photocatalyst, the electron in the valence band can be excited to the conduction band and generate hole in the valence band. So the hole in the valence band can oxidize the donor molecules or react with the water to produce the hydroxy radical. Also, the electron in the conduction band can react with the dissolved oxygen in water to form the superoxide radicals. So these two radicals, hydroxy radicals and superoxide radical, can join the decomposition of the organic pollutant in wastewater to the harmless byproduct or mineralize it into the carbon dioxide of water. So this slide summarizes the advantages of the photocatalytic technologies. So first, the photocatalysis offer a good replacement for the traditional or conventional treatment methods, such as the absorption, filtration, or reverse osmosis, with the capacity for using a renewable and a pollutant-free solar energy. Also, photocatalysis lead to the formation of the harmless product, unlike the conventional treatment methods, for example, absorption like that. And the photocatalytic reaction can be applied in the variety of the different wastewater stream, for example, organic wastewater or heavy metal wastewater, because the electron in the conduction band of the photocatalyst can reduce the toxic form of the heavy metal, for example, chromium 6 to the less toxic form, chromium 3. And the reaction condition for the photocatalysis are mild with the short time reaction, and it has the minimal of the secondary waste generation after reaction. But the limitation of the photocatalysis is about the interfacial charge transfer, and sometimes it has very high recombination rate of the electron and hole, which reduce the photocatalytic efficiency. So they are essential for enhancing the efficiency of the photocatalytic process by using nano materials or nano composites. So as I mentioned in the previous slide, due to the big energy band gap of the semiconductor, it can work only the UV light due to its need the enough energy to excite the electron from the valence band to the conduction band. However, in the normal solar light contain only 3 or 4% of the UV light. The major part of the solar light is visible and the infrared light. So numerous efforts have been made to produce the nanomaterial, such as the nanoparticles and the composites. So this material can enhance the visible ability and effective utilization of the light, which can shift the technology to the visible light of the solar light spectrum. So far, the efforts to produce the visible light in the photocatalyst has been made either by depressing the energy band gap of the photocatalyst material or developing the nano composite. So there are 3 ways to the narrow energy band gap. The first is about doping semiconductor photocatalyst with the single atoms. And the second one is about co-doping by using 2 kinds of atoms. And the last one is about self-doping or defect engineering of the photocatalyst structure. So for the heteroatom doping, the addition of the dopants or the gas atom to the main semiconductor structure will shift the energy band gap either by creating a new state below the conduction band or above the by creation of the new electronic state above the valence band or below the conduction band bottom. As a consequently, the lower energy band gap is required to excite the electron from the valence band to the conduction band. In other words, the doping can extend the spectral response of the semiconductor to the visible light region. So besides that, gas atom doping may affect the electron or hole trap, so it can reduce the recombination rate of the photo-generated electron-hole pair. Also, for more enhancing the photocatalytic activity, doping semiconductor with the 2 kinds of atom that we call co-doping has gained considerable attention due to their higher photocatalytic activity compared with the single element doping. For example, in this slide, I show you about the preparation of the sulfur or nitrogen dope TiO2, and after doping with sulfur or nitrogen, it generates the new trap state above the valence band top, as you can see here in the red line. The generation of the new trap state can reduce the energy band gap, resulting to enhance the visible light ability, also decrease or avoid the recombination of the electron hole pair. So in our research, we mainly focus on the 2-dimensional materials because as I mentioned, if the material has only 1 dimension in the nano size, for example, sheet line or radiolite structure, which has the large size but is very thin sheets, it would be classified as a 2-dimensional materials. And there are many 2-dimensional materials well known as a photocatalyst material such as the graphite carbon nitride, bismuth oxyhalide, layered hydroxide. Also, the clay minerals, for example, Montmorillonite or the saponite. All of them, the natural material or synthetic materials, can be utilized as many applications, for example, co-catalyst, synthesizer, conduction part, or photocatalyst. The most promising property of the 2-dimensional material is the large export active site, which can receive more light and has a more active surface area for the reaction. Moreover, the 2-dimensional materials can provide more the surface contact with other semiconductor or other photocatalysts in the composites, as I show in this slide, in the green one and orange one here. And the contract between these 2 materials can prevent the recombination of the electron hole pair, leading to enhance the photocatalytic activity. So for the photocatalytic reaction of the 2-dimensional materials is similar with the normal photocatalyst. So under light irradiation, it can generate the electron-hole pair on the surface of photocatalyst, and the electron and hole can further react with water or oxygen to produce the active species for decomposition of the organic present in wastewater. So this slide shows some of our achievements about two-dimensional materials and clay-based photocatalyst composite. For example, we prepared oxygen or sulfur-doped graphite carbon nitride, which is an two-dimensional materials. And also we prepared the titanium layer double hydroxide and layer double oxide by heat treatment of the layer double hydroxide. And we use this material for the phenol degradation. So also we use natural material, for example, sapiolite is a pillar clay structure which can absorb the organic dye and use as a dye-sized photocatalyst to decompose organic product in wastewater. So first, I would like to give you some example of our work about the doping of the photocatalyst to reduce the energy band gap. In this work, we published on the Chemical Communication Journal. And in this work, we modified the graphite carbon nitride by adding sulfur or atom into the main structure of the graphite carbon nitride and change the optical property. And we apply these materials for the photocatalytic reaction. So let me introduce you about the graphite carbon nitride materials. The graphite carbon nitride material, or CTN4, has a layer structure similar with the graphite and present the interesting and unique physical chemical property due to their structure have the S-triazine link. However, the electronic and the chemicals property of this material is not so good due to it has very poor conductivity. So recently, the photocatalytic activity of the CTN4 has been attested for various photocatalytic application, for example, hydrogen generation by water splitting or degradation of wastewater, organic pollutant in wastewater. And the problem of this material, the mainly problem of this material is about the combination of the electron hole pair, which reduce the photocatalytic activity. So in this work, we dope the oxygen or sulfur by calcium melamine with the co-precursor as shown in this table. And we successfully prepare the doping sample by shaking XRD FTIR, and we apply this material for chromium reduction. Also, in this work, because if we want to know the generation of the new electronic state or new electron trap state level, we need to use the newly technique, reverse double beam photoacoustic spectroscopy. This technique was produced by Professor Otani in Hokkaido University, and the result of this technique called ERDT pattern, or energy resource distribution of the electron trap. So the pattern of the result pattern, the pattern of this, the result of this technique can show you the electron accumulation density in each electronic state. So here show the ERDT pattern, which is the obtained result from RDB pass technique. And it's clear that the oxygen and the sulfur-doped graphite carbon nitride show the new electronic state level around 2.2 electron volt along here the I point in the blue arrow and the green arrow. The generation of the new electronic state can trap the electron and reduce the energy band gap to enhance the photocatalytic performance and enhance the optical property in the visible light region. Also, we perform the density functional theory calculation to understand the location of the sulfur and oxygen in the graphite carbon nitride structure. Also, we calculate the formation energy of the new electric state by different position of the doping. And it was clear that the more stable of the nitrogen or sulfur were found when the gas atom replaced with the oxygen in the structure of the graphite carbon nitride in the 8th position, which was confirmed by the lowest formation energy, around minus 1.5 for the oxygen and 0.92 for the sulfur. And after doping with the sulfur and oxygen into the structure of the graphite carbon nitride, the middle gap state or the new electronic level between the valence band and the conduction band was formed, which were contributed by the oxygen or the sulfur atom. And the new electronic state is very close to the conduction band bottom, indicate the n-type semiconductor of the new materials. So the DFT calculation can confirm the generation of the new electronics level after doping with the sulfur or oxygen into the graphite carbon nitride, which corresponded to the observation of the new electronic state level in the EDT pattern that I show you in the previous slide. Furthermore, we check the photosynthetic activity of this sample by reduction of hexavalent chromium. It can be seen that the oxygen and sulfur doped graphite carbon nitride show a higher photocatalytic efficiency than the undoped sample. So if you look at in the slide, the black color or gray color is undoped sample, which has lower photostatic efficiency than the blue color or dark blue color, which is an oxygen doped sample, and the green color is a sulfur doped sample. The improvement of the photocatalytic efficiency by doping with oxygen or sulfur may be informed to the enhancements of the light ability in the visible light region and the improve the separation of the charge carrier. Also, we have another work about the morphologies, modification of the morphology of the graphite carbon nitride and co-dope with the oxygen into the graphite carbon nitride structure. In this work, we prepared the oxygen-doped hydroporous graphite carbon nitride by one-pot synthesis, as shown here. So first, the polyethylene styrene ether, or POS, was utilized as a template and oxygen source to produce the hollow structure of the graphite carbon nitride and oxygen-doped graphite carbon nitride. So when we mix the POS with the melamine as a precursor of the graphite carbon nitride, the mixture was calcination at this condition, 500 degrees C for 2 hours, to prepare the oxygen doped holoporous graphite carbon nitride. Also, we vary the content of the oxygen dope by vary the content of the POS precursor. Then we check the phase structure and optical property by this technique, XRD-FTIR or UV DRS spectrum. And also we apply this material for the ciprofloxacin degradation. The ciprofloxacin or CIP is a pharmaceutical drug, and sometimes it can be a waste when it leads to the national water reservoir. And this slide shows the optical property and the energy band gap of all the sample. And it can be seen that the stronger light absorption ability in the visible light region was observed in the oxygen doped sample than the normal graphite carbon nitride in the backlight. The OCN sample or oxygen doped sample can harvest more the visible light and generate more the electron and hole, resulting to more production of the active species. Also, the oxygen doped sample, OCN sample, show the lower energy band gap compared with the CN sample, which is an pristine graphite carbon nitride or undoped sample. So we can expect the decreasing of the energy band gap of the Austen doped sample could generate more electron hole pair under visible light irradiation. And also the modification of the oxygen or doped graphite carbon nitride by POS affect the surface morphology of the sample, which was confirmed by the SEM and the BET analysis. And it's clear that the graphite carbon nitride sample had a smooth surface morphology, while the dope sample or the OCN sample have a rough porous microstructure surface. So this suggests that the modification of the graphite carbon nitride by using the co-precursor of the POS as a template and oxygen source can promote the porosity of the graphite carbon nitride due to the structure of the polymer at a high temperature by creating the pore in the structure. Moreover, the generation of the porous surface increase the specific surface area of the oxygen dope sample, as shown in this table. And you can see in the oxygen dope sample or OCN sample had the high specific surface area compared with the CN sample, which is an pristine graphite carbon nitride. And we observe the morphologies in the lower magnification by using the TEM, and it was found that the CN sample or the pristine graphite carbon nitride show the sheet-like structure. But when we have the co-precursor of the POS or the oxygen-containing polymer as a template or oxygen source, the needle-like structure or tubular structure of the graphite carbon nitride can be observed like this. And the mapping result of the oxygen dope sample show the overlapping of the oxygen atom in the same location of the carbon and nitrogen, indicating that the utilization of the POS as a template and oxygen source can produce the oxygen dope hydroporous graphite carbon nitride. And moreover, we also utilize the RDB pass technique to confirm the generation of the new electronic state after doping by oxygen. And it's clear that the oxygen dope sample show the new electronic state around 2.2 or 2.3, which was lower than the conduction band bottom of the graphite carbon nitride. So the generation of the new trap state can avoid the recombination of the electron hole pair. Also, the DFT calculation of the pristine graphite carbon nitride or CN and the oxygen doped graphite carbon nitride or OCN were performed to confirm were performed to know the new electric level compared with the ELD pattern. And this can be seen that the valence band of the graphite carbon nitride and oxygen doped graphite carbon nitride was mainly contributed by the nitrogen atoms, while the carbon atoms showed a big contribution for the conduction band. And interestingly, the gas atoms of oxygen in the oxygen doped graphite carbon nitride structure generate the middle gap state level around. Here you can see in the late one, right, is the oxygen atoms. The generation of the middle gap state level result to the decreasing of the energy band gap of the oxygen doped graphite carbon nitride sample. So, and also the DFT calculation can confirm the new formation of the trap state by observation in the ELD pattern. And in this work, we apply the preparation samples for the degradation of the ciprofloxacin, which is a pharmaceutical drug. And sometimes, it's gonna affect to the aquatics animal. And so first we mix the CIP solution with the photocatalysis, and then we stir in the dark condition for 30 minutes to make the adsorption equilibrium. And then we turn on the light to to decompose the CIP molecules using the photosynthetic process. And it can be seen that the oxygen dope sample showed a higher photocatalytic performance compared with the pristine graphite carbon nitride or undoped sample. And also the rate constant of the reaction of the oxygen dope sample also higher than the pristine sample or undoped sample. So it can be confirmed that the generation of the new trap state by oxygen gas atom in the structure of the graphite carbon nitride can enhance the photocatalytic performance of the graphite carbon nitride by reduce the energy band gap and avoid the recombination of the charge carrier. Also, the recycling ability of the catalyst was treated, what test and the result of the recycling shown here. And you can see the oxygen dope sample showed higher photocatalytic activity more than 80% for the 5 cycle. In addition, the law of the active species for the CIP degradation were investigated by using a series of the scavenger. And it can be seen that in the presence of the EDTA disodium, parabenzolquinone, or BQ, and isopropanols, or IPA, show the lower photocatalytic efficiency compared with the control, which has no the scavenging in the system, indicating that the whole and superoxide radicals and hydroxy radicals play important roles for photocatalytic degradation of the CIP. And moreover, the excellent charge separation and transfer property of the OCN sample was proved by the photoluminescence analysis and the impedance. And the results show the photoluminescence and the impedance of the oxygen dope sample was significantly reduced owing to the lower electron hole recombination and the high electron transfer. Also, the oxygen dope sample show high and stable photocurrent responsive, which suggests the composite facilitate to improve the light absorption ability and charge generation under visible light irradiation. And also we check the degradation byproduct using LC mass analysis or LCMS. And from the LC mass result, we can find some small fraction of the CIP, which is marked in the red circle, F12 and F10. So the presence of the aliphatic chain carbon, which is the fraction of the CIP, confirm the destructure of the CIP molecule during the photocatalysis. And also, as I mentioned, the CIP is a pharmaceutical drug which may affect to some aquatic animal in natural reservoir. So my collaborator, Meet Yanisa, and I have checked the biotoxicity of degradation CIP solution after photocatalytic reaction by observation of the growth of the E. coli in the presence of the degraded CIP solution compared with the untreated CIP solution and water. So in this slide, you can see the green dot color can refer to the colony of the E. coli. So from this result, it can be found that the no green dot in the presence of the CIP solution due to the CIP is a duct, which might have effect to the prohibit the growth of the E. coli cell. And however, when we decompose the CIP molecules by using our photocatalysis reaction, we can observe some the green dot particle in the D picture, indicating that the significant decrease of the harmfulness of the degraded byproduct or CIP solution after photocatalytic reaction. So based on the previous result, we can conclude that the generation of the new atomic state by oxygen in the graphite carbon nitride structure can reduce the energy band gap and avoid the recombination of the electron hole pair, resulting to enhance the photocatalytic activity for CIP degradation. And another way to improve the photocatalytic activity of the nanomaterial is about the coupling with other semiconductor that I mentioned in the previous slide. For example, the coupling between the TiO2 and the cadmium sulfide, as I showed in this slide, the coupling of these two phases can generate the PN heterojunction of the p-type cadmium sulfide and the n-type TiO2, which is and semiconductor and the photocatalyst. So the heterojunction, the formation of the heterojunction can enhance the electron transfer from the cadmium sulfide to the TiO2, leading to improve the charge separation and photocatalytic performance of this material. So here show the four type, the general four type of the heterojunction. In the type 1, the band gap energy of the material A is steady band gap of the material B. So under the light irradiation, the electrons are excited into the both material. The electron and hole from the material A are transferred to the material B. In this case, the recombination of the electron and hole should happen in the material B. So it's not so good to make this heterojunction because it cannot avoid the combination of the material B. So in the type 2, the conduction band level of the material A is higher than the conduction band of the material B. The valence band level in the material A is also higher than the valence band top of the material B. So in this type is called staggered type of heterojunction. So under light irradiation, the electron are excited in the both materials. The electron can move from the conduction band of the material A to the conduction band of material B, and the hole of the material B can migrate to the valence band of the material A. The electron can accumulate in the conduction band of the material B, and hole will accumulate in the valence band of the material B, resulting to enhance the charge separation and avoid the recombination of the charge carrier by using this junction. And in the type T, the valence band top of the material A is higher than the conduction band bottom of the material B. So under light irradiation, electrons are excited in the both material, but no electron transfer happen even if they have some contract. So the recombination still happen in this both material. And the type 4 is similar with the type 2, but the electron transfer is different. The excited electron move from the conduction band of the material B to the valence band top of the material A. So hole do not move to accumulate in the valence band top of material B. So this type also avoid the combination because we can keep the important electron in the conduction band of the material A and the hole in the valence band of the material B. So we call this one is a C-screen heterojunction. So here I will show you some of our research about the heterojunction of the 2D materials. So in this work, we prepare the zinc titanium double hydroxide, which is a two-dimensional material in the presence of the Montmorillonite clay, which is also two-dimensional clay material. So the Montmorillonite in this case can act as a supporting material, also play the important role for the electron transfer in the photocatalytic reaction. Normally, clay mineral has been known as a good supporting material for the photocatalytic composite. For example, TiO2 combined with the pillar clay, because the clay is a two-dimensional material, it has very high specific surface area and high stability. So it can improve the growth of the TiO2 on the surface of the clay minerals. And regarding the electrochemical property of the clay mineral, it has a large charge density, and natural clay often include the iron content as an impurity. So the impurity of the iron might affect the photocatalytic performance or the photocatalytic reaction. But the problems of the clay for photocatalysis is about the large energy band gap, mostly belonging to the non-electron conductivity material. So normally people believe that clay is just a good support of the main photocatalyst for the wrong year. But in our case, we're gonna show the new law of the clay mineral for the photocatalytic reaction. So we prepare, this slide show the preparation of this composite using the co-precipitation methods. And we have checked the phase component by using XRD technique. And from the XRD, it shows the main components of the composite is the layer double hydroxide, which was growth on the surface of the Montmorillonite clay. And we have calculated the electronic level of titanium layer double hydroxide and the Montmorillonite using the DFT calculation. So for the structure of the Montmorillonite or MT, we have some gas iron impurity in the layer of the Montmorillonite by replaced with the aluminum atom in the main of the Montmorillonite layer. So it can be seen that the new electron trap state can be seen after doping with the iron in the structure of the MT. So this material can act as an important load to transfer the electron from the MT to the titanium layer double hydroxide. Also, the titanium layer double hydroxide, the conduction band of this material was contributed by the titanium, and the valence band was mainly contributed by oxygen. So it's clear that when we add more the iron into the composite, it can reduce the energy band gap of this material from 3.2 to 3.4 to 3.2 electron volt, which may increase the electronability in the UV and visible light region. And we apply this material for the chromium reduction at the pH around 3 because we want to avoid the co-precipitation of the chromium on the surface of the photocatalyst. And it's clear that the composite of the titanium layer double hydroxide with the Montmorillonite enhance the reduction activity of hexavalent chromium, which is a toxic form of chromium. And when we add more iron into the sample in the orange color line, the photocatalytic activity much improved due to the more generation of the new electronic state by iron atoms in the structure of the Montmorillonite and lower energy band gap of the composite. Also, we confirm the charge separation and recombination by using these two techniques, photoluminescence and the photocurrent responsive. So the iron dope sample, the orange in the orange line show the lower charge recombination and the faster electron transfer compared with the pristine layer double hydroxide or CTL. So the nano heterojunction of the layer double hydroxide and iron dope Montmorillonite can improve the photocatalytic chromium reduction via the C-screen heterojunction as shown here. So under light irradiation, the excited electron are transferred to the valence band top of the layer double hydroxide, and the electron are excited in the LDH and accumulate in the conduction band of the LDH. The chromium, hexavalent chromium can reduce by react with the electron in the conduction band of titanium layer double hydroxide or LDH material in the blue side to reduce the toxic form of chromium to the less toxic form, for example, chromium 3+, and some chromium 3+ might can absorb on the surface of the Montmorillonite because of the electrostatic interaction between the positively chromium strippers and the negatively charged of the Montmorillonite. So I want to emphasize our finding that clay is not only support for the main nano photocatalysis in the composite, but also involved in the photocatalytic reaction. So I think we have limited of time. So I'm gonna conclude the work, my talk today. So I want to conclude our finding that the solar light driven chemical conversion of photocatalysis can be applied to the global issue, including environmental purpose, for example, degradation of the toxic organic product in wastewater or air, or reduction of the toxic metal form, for example, hexavalent chromium, to the non-toxic form, divalent chromium. And I would like to emphasize that the photocatalytic nanotechnology is universal and general. It is an emerging field in all the area of the science and engineering or technologies. So finally, I would like to thank my supervisor, Professor Kiko Sasaki, for her kindly support, and my collaborators, Dr. Balakuma and Dr. Kardik, for their support. Also, Assistant Professor Ismail Dabo from Penn State University, American, for his specialist computational simulation, and also Professor Buncho Otani at Hokkaido University, who is a pioneer of the photocatalyst and always suggests me about the photocatalytic research. Also, I would like to say thanks to my photocatalytic group member, and thank you very much for your kind attention.
Okay, thank you, Dr. Chittipon. Your presentation is so fascinating, and yet somehow it contains so many chemistry knowledge to learn, and probably most of our students are not familiar with it. So he got to know that there is indeed nanomaterials have a lot of purposes for environment, which are also useful in our daily life. So we will go ahead and take some time for a question. Now we have a few minutes to answer the question. And for all the students and all participants, just a reminder that please be sure you type your question into the question box in the control panel. So, okay, so I figure out there are some questions. So Dr. So, would you please select the question and read the question out loud and directly answer?
Okay.
From the Q&A. Can you check the Q&A box?
Oh, yes. Okay. For the question from Jawan Rumi, okay. For the first question is how much better is reaction using photocatalysis than using the traditional methods in terms of the reaction speed, increase the percentage, and the waste product decrease percentage. Yeah, actually, if we compare the photocatalysis process with the traditional methods, for example, adsorption, the adsorption process is very fast compared with the photocatalysis, but the adsorption process cannot decompose the toxic protein because it just adsorbs on the surface of the adsorbent, right? But the photocatalysis can decompose the toxic pollutant into the harmless byproduct. Yes, and if we compare with the normal, for example, AOP process, advanced oxidation process, for example, catalytic waste oxidation or catalytic waste peroxidation, the photocatalytic reaction is quite slower than that reaction, because in the photocatalytic reaction, the advantage of the photocatalytic reaction is we don't need to add some strong oxidizing reagent, for example, H2O2 or hydrogen peroxide, to accelerate the reaction, because we just use the sunlight to generate the electron and hole, and the electron will generate the active species by themselves. Right. And what are the requirements for the good doping element? And is there a single base doping element, or is it more depending on what reason? Yes, it's a good question about what is the requirement for the good doping. If we actually, based on my experiences, if we dope so much the gas atom in the main structure of the photocatalyst, for example, if I dope too much oxygen into the graphitic carbon nitride structure, the efficiency will decrease, due to when we dope more gas atom into the structure, we're going to generate so much the electron trap state in the material. So the electron in the trap state cannot go to the reaction. So it's going to reduce the it's going to reduce the degradation efficiency. Okay. Yeah, and actually, based on the doping, because when we dope something, we need to think about the generation of the tap state, right? If we dope some gas element, we can get the N-type characteristic materials. But if we dope others atoms, we can get the P-type. So based on this strategy, we can design the doping elements in the structure of the photocatalyst, okay, or semiconductor. Okay, the question from, sorry, difficult to pronounce the name, anonymous attendee, right? Is correct in terms of, I'm not sure. So what is the difference between the photocatalyst and electrocatalyst? Actually, I'm not familiar with the electrocatalyst, but I think the electrocatalyst can work without light, but the photocatalyst need light to activate the catalyst. Okay. I'm thinking like this, but I'm not sure what the real definition of the electrocatalyst, sorry. And what is the appropriate band gap of some material suitable for the photocatalytic reaction? That's a very good question. Depend on what is the appropriate band gap of some material suitable for the photocatalytic application. Okay, let me show my screen now. Okay, here. Oh, no. Okay, so based on the energy band gap of the photocatalyst, it can distinguish the application, because if you want to do some degradation of the organic pollutants, for example, CIP, pharmaceutical waste, or some phenols, you need to think about the production of the radicals, active radical, for example, hydroxy radical and the superoxide radical. If the valence band top of the photocatalyst is lower than the requirements reduction potentials of the generation of the hydroxy radicals, it can produce the hydroxy radical. But if it not matched with this level, it cannot produce this radical. So based on the reduction potential of the application, we can decide the energy band gap. Yeah, actually, from the equation, the energy band gap can tell us about the region of the light that we can use. For example, if we use the visible light, the energy band gap of the photocatalyst should be smaller than 3.0 electron volt due to the light energies. But if we use in the UV light region, we can use a bigger energy band gap. For example, TiO2 is around 3.2 electron volt, or zinc oxide around 3.2 also. Yes. Yeah, but for the application, we need to think about the level of the valence band and the conduction band of the photocatalytic semiconductor. Right. And then okay, and this question from the Sura-san. Hi. His question is about, could you please let me know what is the effect of the morphologies of some material to the band gap, right? And what is the direct evidence? Can you explain in more detail? Okay, so the easy example of the morphologies effect for the photocatalysis is about the TiO2. Yeah, because the TiO2, we can modify many morphologies. For example, plate light structure, log light structure, or the ball light structure. And when we change the morphology, we might have some defects in the morphologies due to some plane will dominant and some plane will be defects. So due to the defects plane of the morphologies may generate the new electronic state between the valence band and the conduction band bottoms of the photocatalyst. So the generation of the new band may affect the photocatalytic performance. And the evidence that can be confirmed, I think, is about the decreasing of the DRS result, or increasing, I think should be decreasing, to the decreasing of the energy band gap to more visible light region. Yes. And also, yeah, I introduced you about the newly technique, reverse double beam photoacoustics spectroscopy, or RDB pass. This technique can distinguish or detect the generation of the new trap state that I show you, right, in like a histogram graph. Yeah, this technique can show us the electron accumulation in the new trap state. So if you have some defects in your structure by morphology effect, it's gonna reflect by EIDT pattern, and then you can know the location of the trap state. Also, when we change the morphologies, we gonna it might enhance the specific surface area of the photocatalyst. Also, it's a one factor that affect to the photocatalytic performance of it. Right. I think I answered this question maybe. Right. And science data set about this topic. Do you think? It's a good question. Hi. Yes, I think, yeah, nanotechnology is useful for our society now. Yeah. So his question is about, could we make a nanotechnology to build a home, or make a nano plant, or even nano animal? What is a nano animal? So we can live at Mars one day. Artificial Earth. Okay. Oh well, that's a good idea. I think yeah, it's a challenging for our scientific society, right? And I don't know how to answer this question. Sorry. Yeah, I would like to ask a question. What is thing to do when we want to see this material from a metal problem? To do when? Okay, actually, the question from the functions song. What is the hard thing to do when we want to synthesize a photocatalytic material for environmental problem? Actually, now we already some company already apply the photocatalysis for wastewater remediation, like I show you in the photo reactor, right? Yes, and but the problems of the single photocatalyst is difficult to recover after utilization. So we need to make some template, or we need to coat the photocatalyst on the surface on the template when we use to enhance the recovery of the photocatalyst after using. I think yes, this one can solve the utilization or make the more practical application for the photocatalyst. Yeah. So the question from Bastika Sang, graphite carbonatite was doped with oxygen and sulfur. Why you choose this doping? And how about others, such as the boron and sulfur? And how about any other application other than the, yes. The question from Bastika asked about why I choose oxygen or sulfur, why I didn't choose boron and phosphorus, and how about other application of this material? Okay, it's a very good question. Actually, I also have some work that I blow boron and phosphorus into the graphite carbon nitride. But in the deep chemistry, when we dope oxygen or sulfur into the graphite carbon nitride structure by replace with the nitrogen atoms, the oxygen or sulfur have more the valence band. Have more valence electron compared with the nitrogen, right? So it's gonna have one more free electron. So this electron gonna generate the middle gap state, which is close to the conduction band bottom. So this one we call the N-type semiconductor because the neutral state generation close to the conduction band bottom. And if we actually, why I choose this oxygen and sulfur, because it's oxygen or sulfur had the higher photocatholic performance compared with boron, actually for this application. And when we dope the boron is the boron has already 3 electron in the valence electron, right? So when we dope boron, we're gonna lack 1 electron from the system. So we're gonna generate the middle gap state close to the valence band top instead of the valence band bottom. So this one we call p-type semiconductor. So this energy level that which is close to the valence band top, we call the we call the acceptor level. Oh no. We call the donor level. Yes. Right. Okay. And how about any other application other than the chromium reduction? Yes. Based on the position of the valence band and the conduction band bottom of the graphite carbon nitride and oxygen dope hydroporous graphite carbon nitride, we can apply this material for many applications. For example, degradation of the organic product in wastewater. Also, if you want to go to more promising application, for example, hydrogen production, we also can apply this material for that application also. Right. What is the advantage of the graphite carbon compared with TiO2? Yes, it's a very good question also. The advantages of the graphite carbon nitride compared with the TiO2 is the energy band gap of the graphite carbon nitride is smaller than the TiO2. So the graphite carbon nitride can respond well in the visible light region compared with the TiO2, because TiO2 have very big energy band gap, around 3.2 electron volt. So this material is difficult to work under visible light irradiation due to the energy of the light in the visible light is not enough to excite the electron from the valence band to the conduction band top. So the advantages of the graphite carbonate is lower energy band gap, which can work well in visible light region. And in the sunlight has only 3 or 4% of the UV light. So now we want to shift our material to the solar light spectrum. So we need to tune the energy band gap to match with the visible light or the IR. And also the graphite carbonate it's easy to prepare compared with TiO2, just like a calcination of the melamine. So, and it's very cheap, the precursor. So this is an advantage of the graphite carbonate. So it is question, but sir, have you ever think we could make our iris by gold? So it's going to more precise. Why we need to make? Actually, I'm not so familiar with this. Sorry, because I think if we have so much gold in iris, maybe it's not so good for ourselves, right? And hello, my name is Safa. Okay, it's a very good question. The question from Fajar is about how the process to reduce carbon dioxide, right? So recently, the photocatalytic, the application of the photocatalyst is applied for the reduction of the carbon dioxide, because in the carbon dioxide, can react with the host and reduce it to the methane or ethane, which can be the alternative energy source. Right? So yeah, if you want to know about the process of the reduction of the carbon dioxide, I think we should think about the position of the valence band and the conduction band of the photocatalyst. Right.
Okay, so probably it's due to the time limitation. We cannot really answer all the questions, right? So I have one more question as a wrap up regarding the price. Are the nanomaterials cheaper than the non-sustainable materials?
It depends on the materials that you talk there. If you think about the carbon-based materials, for example, carbon quantum dot is very cheap, right? Yeah, I think it depends on the material that you think. If you think about a nanoparticle, it's quite expensive compared with a carbon quantum dot.
Yeah, and about the production, is it already produced in a large scale?
Yes, actually, the nano materials, actually, some material cannot produce in the large scale. For example, metal nanoparticle, right? Due to the limitation of the control of the particle size. But for example, the graphite carbonate we can produce in the large scale due to it's gonna just like a heat of the precursor. Yeah, it depends on the material also. I can say like that. Yeah, but yeah, some material can produce in the large scale, and it can apply for the practical application for sure. Yeah.
Okay, thank you. So it's so interesting topic actually, but again, we need so advanced chemistry knowledge to understand all of this. Okay,
I hope
so
you get some image of it.
Is there anything else you wanted to say before we finish this?
I think I hope you enjoy my talk. I don't know.
Okay, thank you. Great. Thank you, everyone. Last but not least, the committee already put the attendance link in the message box, so make sure you fill it up to get your certificate. And we really appreciate you being here, Dr. Song, and all the participants. Thanks again for joining us today, and we will see you next time. Good morning and have a nice day. Thank you, Dr. Song.
Thank you very much. Bye bye, everyone. Bye, Tan Sang.